Hello everyone. A while ago I created this abstract render in Houdini and thought it would be interesting to make a tutorial to show you how I achieved this look. It's actually really easy to create particle simulations in Houdini and then further enhance them with different attributes that can be used later for rendering. So let's start by presenting how I structured the scene. On the left, there are two nodes, one with the main particle simulation and the other one with the background particle simulation. Then we have some simple geometry which we'll use to instance over the particles. The material network. Then we have two nodes that will actually go into rendering and the Redshift settings, PopNet. We have the camera and the camera focus rig and three lights. So let's go inside each node. As you can see here, we start with the sphere and do some other processing on it. This is the main emitter. Then we have the particle simulation. Then we are caching the particles and do some extra post-processing over them. Next, we have the background particles, where we just have a big cube, scattering some points inside it, and then do some small post-processing to get the final particles. And next, as I said, we have the main instance geometry that will be used over the points. As you can see, it's very simple, but it will catch some really nice reflections. Then we have almost the same geometry for the background particles. I usually like to use custom geometry instead of just simple spheres over the points, even if it's harder to render, but it gets more detailed result. Next we have the two render nodes that actually go into the rendering. One, it's for the main particles. Here we just grab the particles, we instance the first geometry over them, and then we use a Redshift Proxy, which we'll talk about later. And then we do the same thing for the background particles. Then we have the Redshift settings here, which are very easy. As I said, the camera, a focus rig, which we'll talk about later, and three simple lights. The center light that you can see here, and the background light, which is after the particles on the Z direction. It's actually, they're emitting also volume light. Okay, let's start building the scene from scratch. Of course, if you want to support my work, you can find this ready-to-use Houdini scene on my Gumroad page, along with other Houdini assets and tutorials. The link to the page will be in the description of this video. So thank you for that. Here is an almost empty Houdini scene. I just created some placeholders for each steps that we need to go through. And of course, we need to start with the main particle simulation. So I'll create a geometry node, name it main particle simulation or FX. Dive inside and create a sphere. I would need to use a polygon sphere with a lot higher frequency, let's say 100. And let's make the uniform scale a bit bigger, 1.5. Next, what we need to do is to add a noise in order to be able to delete some parts of the sphere. We can do that with an attribute VOP. We plug it in, dive inside, and now we just create a turbulent noise. So the turbulent noise needs the position input, and then we can just use the noise into the color channel. Here I would want to promote the offset parameter, so I can use it later. Okay, here we can just reference the x-axis of the offset to the other axis. And here, because we want to animate this noise, we just need to type a small expression, and that would be at time, maybe multiplied by 0.1. Let's see how this looks. So you see the noise right now, it's animated. I think the speed is too high, so maybe we need to go even lower, 0.05. And now if we play this again, you can see the noise animates a lot slower. Okay, next we would add a mountain displacer. This is a very useful node, and it allows us to add a lot of variation over the surface. Of course, we would need to change a bit the parameters. And I think the maximum octaves are too many, so I'll just go with 1. Okay, and also I want to animate this noise. So here I can write the same expression. It will be at time multiplied by 0.5. Let's see how it looks. So right now you can see there's also the displacement noise that's moving over the sphere and also the color noise in the background. So already this gives us a lot of complexity for the emission. Next, I will need to delete some parts of the sphere. So of course I would use a delete SOP, and here I want to delete by expression, use primitives. I want to use the color to select how many primitives to delete. So let's use cd.x, that would be the red channel. Let's say if it's bigger than 0.02, then we delete everything. So right now you see there's just a little amount of polygons that remain. If we play this, you see the animation is already pretty interesting. Okay, next I would like to delete the color because I don't need it anymore. So I'll use an attribute delete. Also, we can check the geometry to see how much information it has. So you see it's only the position and the color. So the color I no longer need, and I will delete it here. Because it's a point attribute, I can just go here and select CD. So now you see the polygons don't have any color anymore. This is mostly an optimization step. Next, if we look at this polygon, we can see there are not so many subdivisions over it, and the edges are a bit jagged. So let's try to add a subdivide. Maybe it helps a bit. Yeah, so it helps a bit with rounding some corners, not all of them, but I think this will be enough. Okay, next I just need to add some normals that will drive the particle direction. So here we add a normal slope. And I would like to add points normals. I can also visualize them here. So as you can see, all the normals are headed. So as you can see, all the normals are heading on the opposite direction. And we want those emitters actually to emit inside. And there are multiple ways of changing this. I can just go here and say reverse normals. So right now you can see all the normals are pointing inwards. Okay, this is the emitter part. I will just color this as green to know that this is the entire emitter. And then we just need to create the PopNet. We'll put down a PopNet. This is a dynamics network that's already configured for particles, and plug the emitter into the first input. Dive inside, and here we see there are several nodes already configured for us. This pop source defines the source of the particles. Here we see that it already uses the first context geometry. And if we just play this, something should happen. So you see there are some particles emitting on the inside, not really doing anything because they don't have any velocity, but something happens. Okay, now we would need to create some motion. And if we don't want to see those guides, we can just come here and disable the guides. So now we just see the particles. The pop source has a bunch of parameters. So if you go here to the birth tab, we can see that we have the constant birth rate, which are the number of particles that are emitted, and the life expectancy. I won't dial those too much because the default options are good. Of course, I just need to get a lot more particles going on. So let's add another 0 here. As you can see right now, we have a lot more particles. We will need to add a way bigger number here in the end. Now let's create the forces that will move our particles. As you saw in the final image, we would need to move those particles to the center of the scene. So for that, we have a very useful pop node, which is called pop attract. And we can just wire this here into the merge. We can wire as many forces as we'd like here. This pop attract will attract the particles to the center. Actually here you can see the goal is set to 0, which means the center of the scene. And also here we have some parameters. I think we just need to move the force scale to around 4. And let's see what happens. So right now you can see the particles are getting attracted to the middle of the scene, but they also do some funky stuff, and they try to pass over the attraction and come back. So of course we need to change some parameters here. Another thing that I would like to do, not to have this right in the center of the scene, I would like to move both of those maybe upwards a bit. So I can just copy this parameter and reference it here. And if I just maybe put here 0.5, what happens is that the actual pop attract, you can see it here, it moves a bit. So it's no longer in the center, it's upwards a bit. So this makes the simulation a bit more randomly distributed. You can see the particles get attracted not to the center of the scene, but more to the upwards part. I would like to also add some random movement in the particles, and we can do that with a PopWind node. With this, we can add like a turbulence. So let's plug it into here. And here we can just make the swirl size a bit bigger, 2.5. We can also use a guide to see. Oh yeah, I need to switch the amplitude to at least some positive number. So this is the swirl size, and if it was to 1, you see there's smaller swirls. And then we can just use 2.5 maybe, and also the amplitude maybe 1.9, let's say. And now you can already see what the force is doing to the particles. Okay, so let's see how it looks. I will just disable the guides. And now if I play the simulation, you already see that we have a lot of interesting movement here. Maybe it's a bit too random and no one would understand anything. Of course, you can still use this. So you can see there are a lot of parameters, and you can tweak a lot of stuff. So you get a lot of randomness here. I think what we should do is to add like a drag. So the particles are moving, are having a harder time to move in the air. So let's do that. It's like the node is called pop drag. I can add this here. And let's try with a bigger air resistance, let's say 3. And now let's see what happens. So you can see the particles are still being attracted to the middle. They have some swirls to it, but they're not so fast and not so chaotic. So I think we are already getting very close to what we need. In my example, I just simulated 60 frames. So we need to get around here. And as you can see, it's pretty similar to the example that we had. We will also do some post-processing over this. Okay, now we just have one big problem, which happens with particles. So as you can see, after they start moving, you could see some stepping. So here are some particles emitting, then this is the previous one, then the previous one. And this is really annoying. You could see there's like a computer simulated thing. So in order to get rid of this, we need to increase the substeps. And actually what happens here is that one row of particle is emitted each frame, and the frame numbers are not enough for having like a constant flow. So we need to emit also from the subframes. So this is what substep does. It's emitting also in between the frames particles. Okay, let's go back. We can go here onto the PopNet, into the simulation tab, and we see here we have the substeps. I think I used 15 here. So let's see what happens if we increase this to 15. We should already see a massive improvement. Of course, the simulation is a lot slower now. We no longer have that issue where you could see a lot of stepping. Okay, the last thing that we need to do is to increase a lot the particle numbers. I think in my example, I used like 5.5 million particles. I know that seems a lot and it's a bit heavy to calculate, but that gives a very realistic result. So let's try to use that number. So we will put here another 5 and then 3 zeros. So then we have 5,500,000. Okay. As you can see already from the first frame, we have like a lot of particles on each primitive, each emitter. This will give us a really nice feel to the simulation. Okay, to go further, we would need to cache this out. So let's drop a file cache node. I like to customize this a bit. Here we would say just 60 frames, because to simulate 240 frames would take a lot of time. So here we just need 60. I connect this to the PopNet. I already take load to disk to make sure that it loads after simulating. And here in the name, you see there's a quite complicated name. Here I can just change it to something easier. So I would leave this OS. Actually, this variable means the name of the surface operator. And then we would need to use OS again and something like this. So right now what's doing, it's inside of our project file. It's already created a geo folder, and then it's creating another folder called file cache 1 for now. So we just need to say maybe main particles v01. And if we middle click on this, you could see a very long path. So this is creating like inside the geo, it's creating main particles v01, then it's creating again main particles v01 and the frame number. And this is a Houdini extension. Actually, before starting doing the caching, I want to point out that we made two mistakes. One is the constant birth rate. I added one more zero, and that was giving extremely high caching times. Actually, the number is this, 5,500,000. It's a bit annoying, to see it here without the points. Okay, and the second mistake is more for optimization. It's actually that you see here the PopNet has a lot of attributes that we actually don't need, and we don't want to save them to disk to occupy a lot of disk space. So what I did, I added an attribute delete, and here in the properties, this star says that you can delete everything, and then I delete everything besides age, life, and velocity. I don't know if I need velocity or life, but yeah, I just want to have them there. So then we can safely cache the simulation. Okay, if we play the simulation, around frame 60, we see that we have a lot of points now, and it looks really good. If I look at the point information, we have 12 million points. So you should have something around here if you use the 5 million points. As you can see, we just have the attributes that we wanted: age, life, position, and velocity. Now, let's say we want just to random numbers. We just want to fix the frame to 56. We can do that really easily with a time shift. So we add this node here, and what this does, right now it does actually nothing, because it has an expression which is calculating the frame where we are at right now. But if we just delete the channel, we just lock everything to frame 56. So right now, if I scrub here, nothing happens. You can also see there's a clock icon. And right now, because we deleted the channel, there's no clock icon, which means we don't have any animation. So this is really good for performance, actually. Next, what I wanted to do, because we have 12 million particles, I want to actually delete a part of them and use the low number particles before doing the final render. So I can do that with a delete swap. I select points and delete by expression. And here we can delete by modulo. We say, let's say, at ptnum modulo 10. I hope it works. So now it's filtering the points. Maybe we need to, yeah, so right now we have 1 million points instead of 12 million. Let's see if we dial this down a bit. Okay, 2 million. Let's go a bit higher. So modulo 3, let's say. So this is taking the point number and deletes a bunch of points. So now I have 4 million particles. And what we can do, we can just copy this main particle. And right now we just need to cache one frame to disk to use this as a proxy. Okay, so we say here proxy particles version 1. So we just save the current frame. And now we can just add a switch node. We can use the first input as a high geometry, all the points, and the second input as the proxy file. So now we just need to select input 1, and now we have the lower number of the particles. This is just an optimization that we will erase after rendering the final scene. Now we want to build a mask from the center to the outside of the particles to use another material on it. We can do that very easy with attribute VOP. If we dive inside, we can just use the age, which is the incoming parameter, and export it as color. Before doing that, I would like to use a ramp parameter, add it here, and use the age as an input. If I just connect the ramp to the CD, you see something really nice happens. It's actually showing us the age of the particles. And what I would like to do also is to add a turbulent noise to be more random also. So add a turbulent noise. This needs a position, as you saw in the first example. And what I would like to do is to multiply the turbulent with the age. Let's see if it works. Yeah, so as you can see, right now we start to have, more denser color here, where the age is really high, and less denser here. Of course, here we can go into the ramp and change this to a spline ramp. This means that it deals only with luminosity, as far as I know. And what we can also do, we can maybe change the amplitude of the noise. I can just promote this and have it later. So now what happens with the ramp, by default, it's actually defaulting to 0. Okay, and maybe change the amplitude of the noise to, let's say, 3. And now you see it's a lot more powerful around here. What I would also like to do is maybe to change a bit the ramp curvature, to select this and select Bezier curve. So it's we can have a more nicer control here. So you can see it's no longer a linear ramp, but it's like curved one. We can have some fall off here. Yeah, and I want to do this like this. It's easier for me, I don't know why. So you see here, we can really easily control the ramp. Let's say, yeah, we like something like this. Let's say we have something like 0.96 here. And yeah, so something like this, that we have some nice fall off and also a bit of noise variation. So we can use a different material or color differently the center of the particles. What would be nice to do, because right now we are a bit lost in space around here. Let's enable the grid and also hit space age to go to the home position. So as you can see, what I don't like is that the entire particle simulation is somehow upside down. I know it doesn't have a really up and down, but it feels like it's upside down. So what I can do is add a transform, and I can just, let's say, rotate 190 degrees like this. So now it feels like it's standing somehow. Yeah, I think I need to, I rotated this a bit. Let me just check. Yeah, so it's minus 40 here. Right now, we just need to add the p-scale and maybe some extra variation as well. What I would like to do is add another layer of, let's say, noise to the particles. So I can add a attribute randomize, or actually attribute noise, I believe. Yeah, attribute noise. We see by default it's outputting a lot of random colors. I don't want it to output random colors. I wanted to change the position of the current points. So let's see, here we need to type P instead of color. As you can see right now, something really strange happens and the particles are moving into the -X position, I believe. Also, this is looking really interesting, so you can use this one if you want. But what I want to do is just center the noise. So this moves back to the origin, everything. Also, I think what I should do is just copy this parameter on each axis. And now let's say we go with an amplitude of 0.2 maybe. And the element size is actually the noise size. So you see, if I go lower, it has more waves. So maybe let's go even lower, 0.1. We added some extra variation into the position as well. Of course, maybe this won't work for animation, but for static, I think it works pretty nice. Next, what we need to do is to establish the point scale for each point. Right now, I believe it has a random scale, a default scale of 1. We can check that by hitting D and going to the geometry and instead of points, visualizing everything as disks. So what this does, it actually shows the point scale. Of course, it's a bit slow because it tries to display every point. So of course, as you can see, the point scale is very big right now. So let's switch back to points. And here I just need to create a parameter. Let's create a point wrangle. Here we will write a bit of code, but it's very easy. So we say here float because the p scale, it's a float. And we say f at p scale equals to, so we need to do like a fit 0, 1. This is a very standard Houdini function. And then we just need to use like a randomize of a ptnum. So randomize at ptnum. And for the fit, we need to specify a minimum and a maximum value. So we can do that writing here the numbers, or we can just create some sliders. So we say channel float, and here min, and channel float max. Right now, if we hit this button, we see we have two sliders. I think, let's say 0.01 and maybe 0.05 here. Again, we should display this as disks. And again, yeah, they're really big, even if we made them smaller. So what I would do, I would add like a global multiplier, so we don't have to dial here really small numbers. Let's say f at p scale again. And we can say we multiply this with another channel float. So right now the p scale, let's see it here in the geometry spreadsheet. So I can just say p scale. And right now it's 0 everywhere because this multiplier multiplies it to 0. So let's say here 0.2. So now we have a very small p scale, as you can see. So ranging from maximum 0.01 to 0.002. Okay, if we display this as disks, yeah, we can see that right now we are, let's say, on the right track. So we have some the points are actually bigger than what we see here, but I think that will look really nice with the instances that we need to add. So here we say p scale. Okay, now there's only one thing left to do, random orientation for the points. If I select these points and I hit blast and then delete non-selected, we just do this for optimization. What happens if we create a box and copy 2 points? So we input the points and the boxes. So you can see here we have the scaling of the boxes, but the problem is that each box is oriented in the same way. So this creates like a very annoying placement of each instance. Instead of these boxes, we'll place some more interesting geometry. So now what we need to do, we need to create an attribute randomize for the rotation. Attribute randomize, this is a really helpful node. And it's really easy to do that. Actually, we want to have this visible. And here, instead of the color, we want to randomize something called orient, 4 dimensions. So we need to put 4 here. As you can see right now, what happens, so this is without and this is with, we can randomize the rotation of each point and it looks a lot more natural and a lot more better. Okay, this is just for visualization, so we can put this aside. And I think we are done. We will just use a null. And this null, we will name it, let's say, out main particles. And we will use this to reference the particles. Of course, let's not forget about this blast node. I cleaned a bit the network tree. Let's go to the other steps. I think right now we can set up also the background particles, but before doing that, we should set up a camera. What I can do is just create like a camera. And now if we go here and look through the camera, I can just move it backwards. Yeah, something like this. What I also want to do is to change the ratio to a square. We can go into the view and just copy this parameter over here. Right now it doesn't really matter the resolution that you see here because we will override that into the render. Now if we have the camera in place, we can also create the background particles. Let's create a new geometry and just copy this and say background particles, P is from particles, background particles effects, color code this. Go inside and just create a box. We can either scale it from here or we can apply a transform node. Let's change this to polygon mesh, add a lot more subdivisions. Yeah, so I need to move this around here so it's more in the background side. Okay, something like this. Now I can add, just for fun, some mountain displacer, just to create some variation. And then we need to add like an ISO offset. This ISO offset creates volume from the geometry. We can just make it more accurate like this. And now we can use a scatter node to scatter some points inside the... So you can see right now, if I look through the camera, the points are pretty evenly spaced out. What we can do is apply some position change to them. So let's go to attribute noise. Of course, we apply again some color noise, but we won't need that. We just need position in 3D space, center the noise. And right now, let's see what happens with the points. You see they begin to move around. Of course, there are a lot of possibilities to create this. Let's try to view the points a bit better. And then what we can also do, we can just delete some random particles from the background ones. So then we can create a point wrangle. And here we can just type a very simple expression. We say if random at ptnum, it's let's say bigger than a specific number. We can just say remove points. Okay, we have an error here. Yeah, so we need another parenthesis. So now you see this function deletes some part of the points. That's actually what we want. I think this is enough for now. We will see what happens inside the render. So this is very easy to build up actually. Of course, what we also need to do to the background particles is to add the p-scale and the random rotation. So what we can do, we can just go back here and just we can just copy the p-scale and attribute randomize. Now if we visualize everything as disks and we can see they're a bit small now, we can go to the p-scale and just increase this multiplier 1.5, let's say, too big, let's say 1. We leave it like this for now, maybe not so much, 0.8. Okay. Now we add another null and we say out background particles. Okay. If we look through the camera and activate everything, we see that we have the main particles and the background ones. Next, let's create the instances. I'll hide this for now, just for performance. Create another geo node. Name this main particles instance. Dive inside and create like a planktonic, I believe. Yeah, planktonic solids. Here we would select, let's say, not this one. Yeah, this one. I think it looks really nice, like a pyramid or something. Then we would add a poly bevel just to have some more nicer reflections on the render. Here we say maybe, let's say 0.1 and no, or maybe, yeah, maybe we would add 2 divisions and something like this, let's say, or maybe use chamfer. Yeah, I think this is the best one. Okay, maybe 2 divisions. Yeah, like this is perfect. Then we also need to add some normals. So the edges are really sharp. Redshift likes to add this point, no, this vertex is normals to 0. So now we have everything really nice and sharp. And now we just, yeah, let's add an output node for now. What this output node does, it's saying that whenever, if I have the view flag here, it always output this node. We don't make any mistake of leaving a view flag in the wrong position. Okay, next add the background particles instances. We just duplicate the node. And inside here, we will just change the part, this one to maybe, yeah, let's try something like this. We keep the poly bevel and the normals. Yeah, and I think we are done with this. Okay, next we would need to make the render nodes. Let's create another geometry node. Call this RNDR, or at least this is how I like to call it. We would need to dive inside, create an object merge. Here we can just write, it's very easy, we just write obj, and then we have a list with what we want to select. Then we have the main particle effects, and inside we just write out main particles. So this is like a folder structure. Right now we should see the particles. Of course we need to go back to point because of performance. So right now we have the particles here, or we can just navigate through this list to find it. Now I will add a very simple node to instance the geometry to the particles. The node is made by DynStudio. I will present their work later. So right now we can just search for them here, and they have this RS point instance, which is really nice. So we connect it here, and you see it's a very simple expression, but it's sometimes hard to remember it. So we can just say this path here to the pointing to the instance that we want. Main point instance, this is what we want to use. And of course right now we don't see anything, and this is actually the beauty of it, because this is happening only at render time. Probably otherwise it would have killed the viewport, so this is really nice. Let's go back, and here for Redshift it's something like an optimization. Also I want to use like an object ID of 1. This is for rendering for puzzle mats, but in the InstaSync tab I should use Redshift point clouds. It's faster when rendering this kind of massive point cloud data. So actually what happens here is this node actually contains the points, and we'll take this node here that we created, and it will copy on each point actually at render time. It will keep the p-scale and the orientation as we saw with the cubes earlier, but this happens only at render time, and this is really nice. And then we have the render background particles. I think this I could have instanced this manually, background particles. So we just write bj, and here we have out bj particles. So this is really easy. I'll just delete this one and RS point instance again, just to show you again how easy it is. We just connect this one and search for the background particles instance, and we are done. So these are the render nodes. Let's color them with green. And I think before starting to add in the lights, we just need to create another very useful node to focus the camera at some point. In order to focus the camera, we will use a very nice tool that my friends from DynStudio did. It's actually focus point. And what this allows you to do is just very easily add here the camera that you want to use. And it measures the distance from the camera to this point. And very easily it outputs the focus distance here, where we can just copy the parameter, go inside the camera onto Redshift camera, depth of field, enable depth of field, and untick this. And now for the focus distance, we can just paste the relative reference. So now it knows exactly where to focus. This tool is really nice. Actually, you can check DynStudio page on Gumroad. They have some really nice tools, and they also have library, which contains, you know, the point instance that I showed you earlier, and a bunch of other useful nodes. Let's say we want to focus on these threads here. So I think it's where it is right now. It's pretty accurate. To not have such a shallow depth of field, we probably need to lower this down. Let's go to 0.2 for now. We'll see what happens. I'll actually disable depth of field for now. We'll start it later when starting rendering. And we would need also some lights and some materials. So before that, let's just set up the Redshift ROP and see what happens. I will create a ROP network, place it here. It's easier to find it. And here we'll just create a Redshift render ROP. Okay, there was a small error there. And in the ROP here, I just also need to create like an IPR and an AOV, maybe for rendering later. So here I just need to specify the camera, which is already specified camera 1. Here I would want probably to override the resolution on my final render. So let's go through the options really fast. We have here the heap, which is the location of the heap file. It will create a render folder. Of course, I want to change this one and do the same as we did on the file caching one. So we create a subfolder with the OS name. It will have the name of the file here, of the node. So we say abstract blue B01 probably. So here we are all settled. Now I would like to have a per IOV multi-layered EXR. This means that all the IOVs here will be baked into one EXR, and you can access them very easily. Here I just want to drag this around to have the AOVs configured here. And for the Redshift, I would like to enable volumetric scattering because we want to use some volumetric light. I don't need global illumination. And for the optimization, I will use the rather new feature, which is enable automatic sampling. This is an extremely useful feature. I tend to use it all the time now. This what this does, it creates it optimizes the scene for you to render as fast as possible, so you don't need to optimize any sampling here, which can be rather confusing. Let's increase this maybe to 0.1 for a faster rendering. Yeah, I just need to put this maybe to 3.5. This avoids some hot pixels and stuff because the particles are really shiny, so I want to avoid that. Okay, let's set up also some AOVs. I think I need around 4 to 5. Okay, and here in the custom, we'll change this name maybe to mask. We need to remember this for when we create the shaders. And let's hide the options so we have a nice list here. We just need to create the materials and the lights, and we are done. I will create the material network. You can also use the material context here. So in the material network, I'll just create a Redshift material, and this would be the main particles material, and then create another one here. We need actually to assign the material not to the render geometry, which is a bit confusing. We need to assign it to the instances. So basically the instances are those who have the materials and place themselves over the points. So let's go here and we just put this one. And then to the instances, we just put material 2. And now this one would be the main particles and this one would be the background particles. Also, I think I need to enable here actually the object ID. So this would be 1 and this would be 2. And just to make sure for the attributes, I want to specify that I want to extract the CD, which is the color of the points. Well, not for this one, actually for the main particles. So I want to extract the CD. Before starting the render view, I would like to add Redshift DOM light. It would take a bit of time to allocate the memory and everything because the instances are pretty big. So as you can see already, the render looks pretty good. I think you can already leave it like this. And you can see there's a lot of details over these threads of particles. Of course, right now we are just using the lower version of the particles. When we will add more of them, it will look even better. Okay, so let's see how we can enhance the lighting here. Add an Eris light. Probably disable the DOM light. Okay, one other thing to note is that for everything that I do, I'm using the OCIO mode, not the sRGB. So I'm using OCIO with ACES. You can check ACES online. Basically, you download this package with ACES 103 and you just load in the config and use the view transfer as sRGB. And then you also need to use ACES in the compositing software. Yeah, so right now I added this light. We can just move around here because we have the camera locked to camera 1 and move it upwards. I think I would do this with the render stopped because I already know what I want to do. So actually I want to rotate this light and have some light above. And in the preferences, I will make the area size to 2 like this. And now just move it around here, let's say, just to have some light from above. Let's see, like this. Okay, I think this is it. Then I would like to add a light from the center, which would be blue. Let's name this top. Then just duplicate this and make this a sphere. Reset the transforms, name this as center. Of course, this sphere is too big. I just want to scale this down around this. And because the simulation is not ready in the center, I will move this light, just eyeballing it. So I think something like this would work. Now I just want to use a temperature for this light. And if I increase the temperature, it will become blue. But let's start the render and see how everything looks right now. Save the scene maybe before starting the render. Okay, so this looks really nice already. I'll just disable the background particles for now because they're pretty huge. So to do that, I can just type like delete something. Okay. Yeah, well, actually we need to set up the render node. We can do that inside the render SOP. So we go here and go to the object. So right now it's rendering everything that has a blue flag. What I want to do instead is just to render everything that has some RNDR in the name. So I can just delete these candidate objects and put RNDR here, underscore, and this sign. So what means is that everything that has RNDR underscore and some name will be rendered. So this meets the rule, but this one doesn't. So right now even if I disable stuff from here, it doesn't render, only this node renders. So this is helpful, I think, because sometimes you may just leave by accident this one render flag on, and it will crash the whole scene. Let's make the top light invisible and save the scene actually and start the render again. Okay, so I think I also like this black and white. Well, this is really interesting actually. And when I did the scene, I just tested it with materials already, so I never saw it like this. Okay, so I think the top light, it's looking nice. Let's see the center light. Okay, so we can see what the light from the center is doing. Of course, I don't want it to be visible. I just want it to affect the particle somehow. So yeah, it's a bit slow, but yeah, this is how it is with particles. I think it's too strong now, and maybe... Okay, I think we have a really nice start. The third light would be a spotlight for the background. So let's create an RS light again. But this time here we would say spot. Another interesting thing that we can do is set the camera as our target. So we can position it looking at the camera. Okay, and right now, as you can see, it's looking at the camera, so I can just move it around here. Another nice trick that I did with it is enabling the texture, and inside the texture I went here in the there will be in the heap folder, you'll have like an abstract emission texture. So I just placed this here. I think I rotated randomly. Also the contribution scale should be 1 because this is should be affecting the volume. So let's start the render again and see what happens. This light is in the background. We should maybe put it here. Okay, so as you can see, we have a really nice volume light. Maybe we can just dial up the exposure a bit. Okay, and I think this center light is too powerful, but we need to also add the textures to see how it behaves. Now let's create the materials. For the main particles, we would add 2 materials. So let's say RS material. This one would be the yellow one, and I think I used the preset for copper. And then I used, I think, the gold preset, and I changed this. It was, let's say, we need some blue here, so we need to take out the red, and here we would say maybe 0.5, 0.25, and 0.9. So this was the combination that I used. And now we have this copper and blue gold, let's say. We would need a material blender. This allows us to blend multiple materials together. So the copper would be the base material, and then we would have the blue gold as being the second layer. Connect this to the surface, and now we need to bring this color information in. So we would add the RS point attribute, and here we need to say CD with capital C. We will also add a ramp, connect the input here, and connect the blend color here. So right now this acts like a mask between those 2 materials. I think we can already start the render to see everything what happens. So as you can see, there's something happening. Let's just create a render region around here. And yeah, I think we need to tweak a bit the parameters. So looking at the ramp here, let's see what it does. We can debug it. I think we need to make this a lot whiter, so we have a lot of blue particles coming in. Yeah, something like that, maybe more. Yeah, I think we're pretty fine. This center light, it's messing up a bit some stuff. Now we also need to create a special AOV for the mask. So there's a node called store color to AOV. We need to plug it here in between. So this is the beauty input, and the AOV input would be this as a mask. We just need to name it mask as we did in the AOV. So we put this here, and now everything, this mask will be rendered separately on a separate layer, so we can use it in comp. And here we will just we'll just duplicate this material and use this kind of copper. Yeah, maybe with a lot more roughness. Yeah, something like that. Open this one and copy the color code. Set this to IOR so we can control a bit the reflectivity, and put the same code here in the reflection. So something like this. This is very simple material. Okay, let's start the render again. Maybe disable the center light so we can just see what everything else is doing. Okay, so after some small tweaking, what I did, I just changed the center light to be color, not temperature, and set like a dark blue. Also the top light, I changed the exposure to 6. And right now it's a bit confusing because of course you can see that there's a lot more light coming from the center, and that's because a lot of particles are actually erased. Also a thing that we can do to make this a lot more beautiful is to enable the depth of field. So right now you can see that it's making quite a lot of difference here. Of course, the render is very slow. And we can also enable the background particles. Yeah, so now we have the background particles as well. I think they're huge right now. We need to make them a lot smaller. Let's go here into the background effects, hide the other objects, visualize disk as disks. And in the P scale, we can just change this to maybe 0.08 or something to have some really small ones. And yeah, I think something like this. What's also happening is that you see there are a lot of, we are focusing around this point here, and there are a lot of particles that come towards the camera and they're in focus. So what I can do is actually delete some points with this function. I can just copy it wherever I want, let's say here, and say if the position on Z at p.z is bigger than this number, we should remove the points. So yeah, you see something like this. So right now we are just leaving the background points that are all out of focus. So actually no point it will be on focus right now, and we'll just have some depth of field, a nice depth of field to them. I think we are really getting there. Now we would need to switch to the dense point cloud. We can do that very easily. And here, remember, we have this switch. So we just need to put it here. Remember, we have this switch. We just need to switch the input from 1 to 0. And of course, we don't want to leave the points as disks. So now if we check the geometry spreadsheet, we have 12 million points. And let's pray the Redshift doesn't crash. We can just view them here. And one extremely important thing would be that we can export this as a Redshift proxy. So to do that, you can use my utility that you can find on Gumroad. It's called Redshift Proxy. This is a really easy utility where we can just add it here after we instance the points. We can enable it, and here you have the same heap folder. We can just type here geo probably, and let's rename this to particles proxy. And now what I can do, I can just render to disk, and then it automatically loads up the proxy. The benefit of doing this is that the viewport will be really fast. Redshift loading times will be faster, and also rendering times will be faster. So please make sure you check this utility on my Gumroad page in the description of the video. Now I hit use proxy file. As you can see what happens, it replaces the particles with this box. You see the viewport performance is extremely good. Now if I just go back and start the render view. Okay, so as you can see, we have a bit different image than what we had in the cover example. This is because we used a lot of random expressions and building this randomly, but I think this one looks also really good. I just maybe need to tweak the center light to be even more less visible, -4 here. So this is the core. Of course, these particle renderings, abstract renderings have different results each time. So I think I also really like this image. Of course, here we also have the mask, which you can use in the composting software. Then we have the specular, the reflections, the puzzle mat we cannot really see now, and also the volume that we cannot really see now. So those are some useful AOVs that we can use. And the last thing would be that we also use a denoiser. So let's go into the PopNet, and here in the Redshift output, we select denoise, and here we select Altus dual pass. The Altus denoiser, it's integrated with Redshift now, and it's really, really good. I like the dual pass mode because it gives better results. Here I would also save additional buffers and do not denoise AOVs for now. And what I can do is I can just start a render to see how everything works. I think for the settings here, I can go maybe 0.085. And now let's see if I start Redshift in bucket mode, I will only test it on a partially zone. And let's increase a bit the resolution also. Override camera resolution, and I can specify the resolution here. So let's use something like this. And now let's start the render again. Now we are in progressive mode. We need to change it to bucket and see what happens if we are okay with the denoising results. This is the render with the denoising. As you can see, it produces a really nice result. Actually, if we have a look at this AOV, which is the noisy beauty, we can see how noisy it actually was if we rendered this without the denoiser. So now it's a lot more cleaner. Of course, what I usually do, I tend to add a bit of this pass over just to have just a bit of noise in the end. This is the final result from the tutorial that we did live. As you can see, it's a bit different from the cover image, but personally I like both. It's also because we use a lot of different random parameters, and with this kind of abstract stuff, we always get different results. If you found the tutorial useful, don't forget to subscribe to my channel and check out the links in the description of the video for future content. Until the next time, stay safe.